Welcome to the Wiggly Wire Automation channel. Thanks for joining. I'd like to talk about Modbus today. Specifically, we're going to walk through how to set up Modbus in Automated Logic's web control platform. This video is part of a larger series on Modbus and how to work with it across many platforms and environments. This one is specific to ALC, but the fundamentals will be the same for any type of device using Modbus. What will be different is the user interface and minor device behavior, both of which we'll be examining here today. This isn't a deep dive into Modbus theory or the technicals. It's a practical walkthrough for setup, configuration, and checking your work geared towards the on-site technician who is probably not getting the support that they need. I'll show you how to configure an ALC device as a client and as a server, although client mode will be far more common for your use case. I'm including both client and server configurations to be thorough, as well as reinforce the relationship between the two and how Modbus works in general. After we explore the setup in web control, I'll use Modscan to check our work and interact with the device to show different perspectives. All right, let's jump in.
I've made a small demo network of just 2 devices for this video. I've configured an OFBBC as the Modbus client device on TCP IP and as the master on the serial Modbus RTU network. The second device is an OFBBC NR set up as the Modbus server and slave device respectively. Let's quickly look at a Modstat. This is one place you can see the Modbus integration points used and the capacity. You can also see what the current status is of the serial ports. On the driver page, you can also see that Modbus integration points capacity. Going into the BACnet router properties page, this is another place you can see the status of the serial ports. On the communication status page, you can view the protocols that are currently running, with Modbus TCP IP at the bottom and the serial ports above that. Modbus serial is where you'll set up serial communications. As port S1 is set with the rotary dial on the front of the controller, you just see enable disable for port S2 as that's software configurable. You set the baud rate here, and then you can set as master or slave. For Modbus TCP IP, the way you enable it is using this drop-down menu, with none selected meaning disabled and TCP IP meaning enabled. Client is much different than server. Below that is the error definitions page for when you run into errors on your network points page. You can cross-reference those here. The server has the same configuration options. On serial, it will be a slave and the address set accordingly. Of course, the baud rates have to match. On the TCP IP side, it will be a server. If you plug into the service port and go to 169.254.1.1, you'll see another way to view the Modstat and do basic network configuration. What's neat about this is in the later firmware versions, there's actually quite a few features under the service port access, including this dedicated Modbus tab. This shows us the Modbus TCP IP and serial settings just as you would configure them on web control. This can be useful if you don't have access to the server. Now that we've covered the fundamental device and network configuration settings, let's move to the next step of determining what data we need and how to get it, and some of the ALC specific nuances. I'll start off by looking at a generic Modbus device for its memory map. Then I'll go over the sample memory map that I've made for this demonstration video. You'll be spending a lot of time looking at these data sheets, which are essentially a large spreadsheet of how the data is organized. You'll see the register index, in this case 40,000, which is zero-based. You'll see the description of what that data holds. Hopefully it's a good one. You'll see the data type. And then lastly, you'll see if it's writable or if it's read-only. So for example, if we wanted the internal temperature, we'd find that in register 40,011, and we know it's unsigned, and then that would be read-only. Then let's look at our demonstration memory map that I've made here. I've used all of the register types and populated them with sample data. The coils start at 1 and increment by 1 bit each. The discrete inputs start at 10,000 and also increment by 1 bit each. The input registers are read-only on the analog side. They start at 30,000 and each of their registers is 16 bits or 1 word wide, with the floats occupying 2 consecutive registers. So that's why this jumps from 1 to 3, but this is 3 to 4. The holding registers follow that same rule. They start at 40,000 and each of their registers is 1 word wide. Also of note here, even though coils and holding registers are usually read and writable. I've made this distinction for automated logic that for a register to be readable, it must have a network output attached to it. So this is the memory map that the server would host, and this is what the client has to poll. Now that we've laid the foundation with proper device and network configurations and studying the reference memory map, let's look at how to bring the data into your integration program. Remembering the perspective of the client-server relationship, I'll start off with the client-side demonstration program. At the top, I've listed the building blocks to use for framing out your program. The coils are optionally bidirectional, so there's one of each. A BNI for reads from the server, and a BNO for writes to the server. For both the discrete inputs and input registers, these are read-only from the server, so they are unidirectional. Similarly to the coils, the holding registers are optionally bidirectional. Down below, I've used those building blocks together with dummy logic to sketch out the sample program based on the demonstration memory map we saw earlier. I've also labeled each network point with the address to be populated on the network points page. For coils, I've got two of each, 2 writes and 2 reads. For the discrete inputs, 4 reads using BNIs, same with input registers, 4 reads with ANIs. Lastly, the holding registers also have 2 of each. Let's look at the corresponding server program. While this shows how to configure an ALC device as a Modbus server, which is quite uncommon, you could imagine the server being any device of any brand. Imagine this as a behind-the-scenes perspective of the server, how the variables are updated, and how it links to the memory map. Let's start again at the top with the building blocks used to frame out the program. This is how you tell the device where to put variables within the Modbus memory map and assign read and write access. A coil can have a write from a client, or display a coil status as a read-only variable done with BNI and BNO respectively. The discrete inputs and input registers are read-only, only corresponding to network outputs. The holding registers are again bidirectional. Down below, I've again used these building blocks with dummy logic for a sample program, which directly represents the demonstration memory map and is symmetrical with the client program. I've again labeled each network point with the address on the server side, telling the controller where in memory to store each variable, which then will be the location that the client references. For the coils, these can be written to by the client, or the server could have its own internal logic to turn the fan on. For the third coil, this is both overwritable from the client as well as displaying a read-only status, declaring that the boiler has been commanded on. Note that for both the input and output, it is the same register, in fact, the same address string being used, with the only difference being BNI versus BNO. The last coil is read-only for the hot water pump. The discrete inputs are all read-only. Same with the input registers. For the second variable, I'm using packed bits to send an error code. If there is no error, then the value is 0. If the fan fails, then the value is 1, indicating bit 0 is on. Let's quickly jump back to pay special attention to where this is being referenced in the client program. In the discrete inputs, I'm taking bit 0 and bit 1 of register 30,003, pulling those bits out of an integer, as well as the whole integer being retrieved here. For the holding registers, these are inputs, so they are overwritable from the client. The third one is readable and can also be read, and this last one is read-only. This is a cheat sheet from Modbus address formatting in WebCTRL. The general address string is Modbus port, register type, register address for the server. The client adds the device address at the end. The Modbus port for TCP IP is simply M TCP IP. Modbus RTU has 3 variants depending on the port being used. Port S1 and S2 each have a dedicated Modbus prefix. Simply Modbus can be configured to either port S1 or S2. For the register types, the keywords are DO for coils, DI for discrete inputs, and SYNT, UINT, and float on the analog side. The clients have a few more options, with bit N available for direct bit access. There are also 32-bit variants of SYNT and UINT. The register addresses are provided by the vendor in the documentation, and ALC supports 6-digit addressing. For device addressing, it is simply the slave MAC address for Modbus RTU. For a TCP device, that device number will be 0, followed by the IP address of the device. For an RTU device under a Modbus router, it will be the slave device MAC address, followed by the router IP address. Things to watch out for: 32-bit variables occupy 2 consecutive registers, skipping numbering. And WebCTRL is a 1-based system for addressing. Also, Automated Logic does not support 64-bit registers. On the left, I've got the client program open, and on the right, I've got a vertically oriented copy of the same memory map we saw earlier. I've also populated here the network addresses that were commented in the programs we looked at earlier, and we can see the direct relationship and how these are derived. Let's look at that same view from the server side. So let's see these side by side to compare. I've got my comms enabled on both sides. On the server side, these will all say initializing until they receive a poll. At what point they receive a poll, they say no error if there is no error. Now, this is an input and has not received a write from the client, so this still says initializing. On the client side, they will all say no error unless there's an error. And we've got a few. So let's go through these and see what the problem is. So I've got unable to connect, an address error, and an illegal data address. I've got the IP address wrong. So it's trying to poll a non-existent device and is getting no response. So when I correct the IP address here, this should go to no error. In this one, I'm trying to poll a discrete input of address 1001, but that's not possible because discrete inputs start at 10,000. I missed a 0. This one is something, again, just watch out for those floats. Those are double wide. So at 30,006, there's a float, which means that occupies 6 and 7. The next one I can poll is 8. So now we've got no error on all of our client and server side. We can start interacting with these to make sure that they work the way we expect. So this first one is a fan override. So it's a B&O. If I lock this on, we'll see this turn on here. What's different about the fifth one, for example, I've got a BNI and a B&O, and these are both going to the same register. So if I turn 5 on, this output will turn this input on, which will turn this output on, which will turn this input back on. So this is the read of this write, effectively. Now, all of these discrete inputs are read-only, so we'll manipulate those on this side. And these are all network outputs here. And we'll watch 1, 2, and 6 turn on over here. Now remember, these are bit 0 and bit 1. Bit 0 right there of 30,003. So this one's putting out 4, which is bit 2. So if I change it to a 1, I'll see the 0th bit come on. If I change it to a 2, I'll see bit 1 come on. If I change it to a 3, I'll see them both come on. Now let's say the hot water supply temperature is 110. Let's say the return is 93. That's just as we expected. These holding registers, this first one's an input, so let's set the room set point to be 74.2. Let's make that fan 50%. Now going down to number 6, if I set this to 55, I'll see that reflect back here because these are the same register. So there you have it. That's how to set up a client and a server and how to check your work in WebCTRL. Let's examine our server program via Modscan. So we'll connect with the IP address. Right off the bat, we see an exception response. Well, the problem is address 1 is write only. If we shorten this length to 1 and we increment, we see that response goes away at coil 3, which is tied to a network output. If I lock this off, that changes to a 0, as we'd expect. What's interesting is via Modscan, you can actually write to a network output. So I can override it, the input and the output. Going back to address 1, it shows an exception response, but we can still write to it. So we'll turn that one on, and we'll see this turn on here. Moving on to the inputs, I will pull a length of 6, and I'll force these on, and we'll see that immediately. Going to input registers, we see an exception response because we're pulling a length of 6. This float is 6 and 7. We're trying to pull half of a float. So if we lengthen this to 7, that response goes away. If we force these values to something else, we'll see them populate on this side. Go to holding registers, and again, these will show that same exception response. And we can confirm that by going to this network output, which is on number 5. We'll change it to a 5 there, change this length to 1. That message goes away, and we see this value come through. I can go to number 3, which will give me an error response, and I can change this to 45. I see that value come through as expected. So we've confirmed all of our values via Modscan.
That wraps up this demonstration of Modbus in web control. I hope you learned a few things. I even learned a few things making this video. I look forward to your comments and feedback. Let me know if there's anything I missed or recommendations of another topic I could record. I really appreciate the engagement.